Hey y'all. Okay. Before we get started, so instructors didn't get, have you seen me dress well ever in this class? I mean, this is a pretty rad sweater, but yeah, I've given up here. So I didn't get this letter about SNS grading, but I've now seen it. I just want to confirm my understanding. So I was asked to not make this class SNS, because stat majors need a numeric grade for it. Am I correct that y'all can now just make this SNS after you receive your grades if you want, and you'll still get credit for the stat major?
Yeah, so we can SNS any class. There's no limit to the number of credits we can SNS, and any class we SNS counts for major requirements.
Okay, so you can, as the kids are saying these days, yeet this class if you choose to.
Yeah.
We can even do this next year. Like, we can really just decide to make this SNS next year, I think. Like,
Okay.
it doesn't matter at all.
That was my understanding, is that they have just totally opened it up. Okay, so I'm glad I understand that. I'm gonna wait for one more minute until people join to address that issue. But yeah, good thing. Okay, I'm glad that they did that, and that makes my life easier and your life easier. Oof. Yeah, not an ideal into the quarter for any of us. I'm sure getting that email was somewhat relieving. Before I saw that email, I had planned to. My initial plan was to basically make this let you choose whether you wanted the final project to be 25% of your grade or 10% of your grade, but I don't think that's really even necessary anymore, given this SNS email. So yeah. Okay, so we're at 3:31. Hopefully more people join in. Let's see. So to start out, okay, so first of all, addressing this SNS grading policy. So it sounds like everyone can SNS this when they basically whenever they want to, which I support. So yeah, so the final project is still going, and it's still going to happen. So what I'll say on that matter is that I understand that some of y'all may not like complete the project kind of to the standards that were set when I assigned it. And I'm okay with that. I kind of I accept that, and so what I am going to, like, when you turn in your project, I'm just going to read it sort of dispassionately and non-judgmentally, and I'm going to award credit for the things that you did, right? Even if you didn't complete kind of all of the aspects of the project. So what I would just ask on your end is that if you find yourself in a situation where, for one reason or another, you're not able to kind of complete the project to your satisfaction or meeting all the requirements of the project, you can just sort of be upfront about it. So if you're not going to hit the word limit, for instance, don't write a bunch of extra words, in order to try and meet the word limit. Because, like, I'll know, we can usually tell when that's happened. Or if you don't have a time to do, to appropriately use a new model, right, that we haven't learned about in class, there's no reason to try and throw something together at the last minute, right? I'm going to, if you don't use a new model, but you do use a model that we used correctly in class, like that is going to be, you're going to receive a solid share of points for that. Yeah, I don't want to like totally cancel the final project or anything out of respect for the people who started the project and early and and have put in some work on it already. But I think that if we haven't already communicated about about your grade in this class, and if you saw my email from a few weeks ago and you saw that you're probably you're probably on track for a good grade in this class, the final project is unlikely to change that. So by all means email me if you are worried about your final project or your final grade in this class. But if you were on track to receive a grade that you wanted in the class, and you and you do the final project sort of incompletely, but you turn something in that has the basics there, that analyzes the data, answers a couple scientific questions, you're going to be okay. Okay. Let's see. Okay, so the second housekeeping thing is course evaluations. So those got sent out earlier than I wanted them to by the department, but that's okay. I think you have until either the 5th or the 6th, so Friday or Saturday, to complete those. Normally when I'm teaching, I have those evaluations done in person because it's extra important. I'm going to go ahead and argue that it's extra important that you fill those out for me as opposed to your professors who are full professors with PhDs. My goal is to get a teaching job where my main job is teaching college students, right, for the rest of my life. And so it's particularly helpful that you provide detailed comments, right? Not like you can right, that you provide comments that if they're positive and there's something that you liked, what with a particular thing that you liked, so that I can keep doing that when I teach. If there's something that you didn't like or that you think needs changed, you specifically say what that thing was. So I acknowledge that there will be negative comments, right? Like maybe some general comment about the organization level of the course could have been improved. I acknowledge that, but more specific comments about what you liked or what could be improved would be really helpful, both in terms of me improving my teaching, and also because I'll be applying for jobs in the fall, and so having like a high response rate for teaching evaluations, right, and having some comments to show to universities that I might be trying to get a job at, that allows them to do a better job deciding whether to hire me. So your evaluations are gonna count for more. Like they're gonna help people make decisions more than for your tenured professors who are, right, some of your professors, they're just gonna keep doing what they're doing no matter what you say, right? So please go ahead and do those. Okay. So also, I said this at the beginning. If you weren't here on Monday, what we're covering this week, I kind of threw what I had planned out the window, and what we're covering is algorithmic fairness and discrimination, and how we statistically analyze and talk about fairness and discrimination. It's the lecture's a little more informal than it has been in the past, and so yeah, so if you have been maybe feeling a little, if you've been feeling particularly lonely over the last week, or perhaps a little afraid or uncertain, remember that you're welcome to turn on your video so that you can see each other and be seen by other people. Not asking you to, but that is an option that I'm always okay with, and I'm not going to get all distracted if you turn on your video in class. So that's an option. Okay. I'm gonna I'm going to hop into the lecture, and we can talk about, the lecture will only be an hour, right? So there will be plenty of time at the end of class for questions or for you to get out of here early if you want. Okay, here we go. Okay, so hopefully all of y'all watched the recording of Monday's lecture. If you didn't, let's just, just speed through the slides to, to just briefly get you up to speed on what happened. So we talked about different types of discrimination. We talked about direct algorithmic discrimination with this kind of just really obviously racist algorithm that is usually not going to be employed in practice. This algorithm that just hires someone if they're white and otherwise doesn't hire them. And then we delved more deeply into the idea of proxy discrimination, which is much more pernicious and important, right? And so the idea of an algorithm that, rather than discriminating directly on the basis of race, takes into account someone's name, right, which can be found on a resume, and perhaps the racial connotation of your name, right? Like whether you're named Chad or Jamal or Zauchi or whatever, right? There's going to be a way of right, your name is going to have racial connotations for people, and so perhaps discrimination can occur through that, but not literally directly on the basis of your race, right? And so this happens in the real world, and there are very clever studies done by people to try and detect it. So we talked about that a little bit, and then a couple more examples of proxy discrimination that are very prominent. So one is redlining, where zip code is used as a proxy for race, or was used as a proxy for race back in the 1930s in order to systematically deny federal mortgage loans to Black people. And then also in college admissions, where this lawsuit by the Students for Fair Admissions group sued Harvard University, arguing that the admissions process discriminated against Asian students largely by proxy, right? That the admissions process didn't necessarily directly say, oh, this student's Asian, we don't want to admit them, but that metrics such as well-roundedness or uniqueness were used as kind of perniciously used as proxies to try and bring the number of Asian and Asian Americans admitted down. So then we hopped into how do we prevent this? And we saw that this idea of fairness through unawareness, by just not using race in the decision-making process, is almost always kind of insufficient to ensure fairness. And that sometimes, in fact, explicitly considering race is the only way, right, to guarantee fairness. And so we went through a simulation study that I'm not going to redo right now. You should watch Monday's lecture if you haven't, if you're interested in seeing a real kind of mathematical and statistical example of how this can happen. But we saw a simulation study about car insurance, where the only way to ensure that Black folks weren't being overcharged for car insurance was to explicitly use race in the insurance company's model of how risk prone different people are. So a very counterintuitive situation. Yeah, so this was that. And then we talked about, and then we saw that, okay, well, maybe there are some cases where fairness through unawareness can work. So we talked about this little example of hiring translators, where in this model, taking into account race may be unfair, right? So it's not a clear-cut situation where you can just do the same thing every time in every situation and avoid discrimination. Okay, so that's where we stopped on Monday. And so today we are going to press onward here. So to start out, actually, so before I keep going, are there any sort of clarifying questions that people have who saw Monday's lecture about any of the stuff that we covered Monday before I move forward into new stuff? Okay, so let's go onward. Okay, so another issue that complicates algorithmic decision making and fairness is the idea of thresholds. And so I'm going to go shut my window because someone's mowing outside. Okay. It's still really loud, but whatever. Okay, so we're going to analyze yet another situation, another example where algorithmic fairness is at issue. And so this is in modeling recidivism. So recidivism is a word that means criminal reoffense. It means so if you recidivate, it means that you commit a crime that you have already committed before. So judges, after a defendant has either been acquitted or convicted, right, found guilty or not guilty of the crime, actually take that back. So there's two decision points that judges have to negotiate that we're going to talk about. So the first one is before the trial, right? Before the defendant is acquitted or found guilty, and that is posting bail. So a judge can allow a defendant to leave jail and go do whatever until the trial, right? They can say, okay, like, we arrested you, we booked you, we are, you're going to go to court to see if you, to see whether or not you were guilty of, shoplifting, right? But we're going to let you go, right? We're going to let you leave jail and go about your business until the court date. So the judge has to decide whether or not to do that, whether or not to allow the defendant to go free until their court date. And often the way that works is the defendant has to pay money in order to leave jail. So it's called posting bail. So sometimes the defendant's friends or family will come and pay the bail money so that the defendant can leave jail. Now we could spend a long time talking about whether that's a reasonable system and whether that or not that's a fair system. Whether you should be whether having money should be the basis on which you're allowed to have your freedom until the court date. But that's what happens. The second thing that happens is parole. So when you're imprisoned, you can be put on parole, which is basically being let out of jail early on some conditions because you're predicted to behave well. So you'll be let out of jail. So hopefully most people here are familiar with the idea of parole, but you go on parole, you're not allowed to leave the state usually that you were imprisoned in. You have a parole officer that you have to check in with regularly to make sure that you are doing okay, and that you are, that you're behaving safely and obeying the law. But you can get out of jail early on parole. So both of these things are decisions that have to be made, and recidivism, how likely you are to reoffend, right, once you are given your freedom, is one of the primary, right, is kind of one of the main things that is considered when making these decisions, right? If you have a low risk of recidivating, then letting you go free may be a great idea. If you have a high risk of recidivating, we may not want to do that. Okay, so, right, we want to, and so recognize that this is an enormously complicated topic and that there may be underlying flaws in the system that we're just not going to discuss right now. But, right, we're kind of taking the system as it is and addressing this one point. So, right, the idea is we want to do this as accurately as possible, right? We want to let people who are unlikely to reoffend, we want to let them go until their trial, right? We want to put people out on parole when they are unlikely to reoffend criminally, right? To, you know, reduce the usage of jails and give people, right, an opportunity to get their lives going again, right? That's kind of the argument. At the same time, we don't want to let people who are highly likely to reoffend, maybe we want to keep them in jail until the trial. That's how the system works right now. And we can actually do this, as you may have guessed, with a statistical model, like a logistic regression, right? We may have, right? I mean, the thing that we want to model or get a handle on is the probability that someone will reoffend, right? If they are if someone posts bail for them or if they are given parole. And as you are also all now familiar, the way that we would fit a logistic regression is we would get data on whether or not people have reoffended, right, in the past, and also covariates, things like age, how many prior offenses they have, the types of prior offenses they have, mitigating factors, perhaps, and also things like race or gender or age that are probably, you know, that are somewhat, it may not be obvious whether these are things that we should include in these models. Okay. Okay, so the thresholding idea that makes this difficult is kind of conveyed on this slide that I saw at a talk at a fairness workshop last summer by Shard Goel, who's a computer scientist at Stanford. So consider two groups of defendants. The top group are Black defendants, and the bottom group are white defendants. Now there's numbers below each of these people, which is the model's estimated probability of reoffending. And in both groups, the average, right? If I randomly selected a Black defendant or a white defendant, the probability of the average probability of reoffending that I would get is 40%. There's a little typo in the bottom line here where this 0.3 should be a 0.4. Just kind of ignore that, it's not important. Okay, and so in both of these groups, the rate of reoffense is 40%. However, as you are all familiar, we have to make a decision, right? Our model has to make a prediction. It's not enough to say, oh, these are the estimated probabilities. We then have to go and say, well, we should let this person go out on bail or not. We should let this person go on parole or not, right? Detain means not let them post bail, means keep them in jail. So we have to come up with a prediction rule, right? A threshold that is basically, right, it's of the form, you know, detain if estimated risk or probability of reoffending is greater than some cutoff. I hope this is sounding extremely familiar to everyone. It was on the last homework, for instance, right? So we have to do that, and we want to do that fairly. So say that we detain defendants who are more likely than not to reoffend. Maybe that seems like a reasonable cutoff, right? If your probability of reoffense is greater than 1/2, then we're going to detain you. And in this example, this means that we detain 5 out of the 13 Black defendants and none of the white defendants, right? So even though Black and white defendants are going to reoffend all at the same rate on average, we're detaining a bunch of Black defendants and no white defendants. How could this happen, right? What would happen? How could we end up with a model where the white defendants' estimated probabilities are so consistent, just a little bit below that 0.5 threshold, and the Black defendants' probabilities vary so much? Well, let us see. Okay, so this is gonna, for those of you that saw Monday's lecture, this should look extremely familiar to you, the setup. So we'll let there be 1,000 Black and 1,000 non-Black defendants here, right? So that'll be our vector A, right? A is going to stand for the sensitive attribute, so it's going to stand for the race of the defendant. And then in this example, we're going to generate two variables, X and Z, that determine the riskiness of reoffending for people. So you could think, I'm going to keep it abstract here, but you could imagine that X and Z are, oh no, this person's right outside. God, okay, I'm just going to go to my room for a second. Sorry about this, y'all. This lawnmower's hella loud. Okay. You get to see my sick Jimi Hendrix poster while I lecture. Okay. Hopefully that goes away soon. Okay, so back to this. We can imagine that X and Z are maybe things, metrics like their scores for how many prior offenses someone had, right? The number of prior offenses or prior convictions that you've had probably influences your likelihood of reoffending. Or maybe their age, right? But we're going to keep them abstract. So they're going to be generated as you see here, X and Z. And what you'll notice, right? So they're normal random variables with mean 0, right? So their means do not depend on race. However, for X, the variability does depend on race. So A equals 1 corresponds to black folks, right? So for black folks, the standard deviation is 1, which means X is going to vary, right, if you're black. However, if you're white, A is 0. So there's 0 variability, which means if you're white, X is always going to be 0. X is always going to be 0. Z, on the other hand, is going to have a standard deviation of 3 for everyone. So the averages of X and Z are going to always be 0 for black or for white folks. But the variability in X is going to depend on your race. Okay, then I've got my xfit function, which I hope everyone is familiar with. And the way I'm going to generate Y is I'm going to make it a binary variable whose probability of being 1 is xfit of X plus Z. So I'm basically, what I'm doing is I'm doing a logistic regression model in reverse, right? I'm generating the data from a logistic regression model. Don't have to do all the math in your head for that right now. Just take my word for it. Okay, so as the software developer or the statistician in charge of the algorithm that the court is going to use to decide whether to detain people, I'm going to have a choice. I can regress I have some historical data of folks that that offended or did not offend, right? I've collected data on past criminal defendants, and I have a choice of which covariates to put in my model, right? I've collected all this data. Some of it I can put in my model, some of it I can't. So let's compare the model where we regress on X, right, which is the variable whose standard deviation depends on race, versus the model where we regress on Z. Okay, and then I'm going to generate a bunch of test data, right, because we care about predictive power, from the same exact way. And then I'm going to get my predictions out of the model. And I'm going to do it, I'm doing it manually here, just, I don't know, I like doing these things manually sometimes. So I'm not using the predict function, I'm just taking the coefficients out of the model, multiplying them by the covariates, adding them up, and taking the xfit for the X model and the Z model. So let's see what we get. So here's the histogram of the X predictions. What you can see, right, is that there's a huge peak at 0.5 because half the folks in the data set are white and they all have X equal to 0, right? R norm with mean 0 and standard deviation 0 means I'm always going to get zeros. And if I do x bit of 0, I get 1/2. Okay, so these people are all 50-50. And then for the black folks in my data set, I see that I have variability, right, in the predicted probabilities of reoffense, in the predicted probabilities of reoffense that is centered at 0.5. Okay, so now let's compare that to the predicted probabilities based on the Z covariate. Very different looking, right? So first of all, we don't see any weird behavior because there's no difference in how Z is generated for black and white folks. The second thing that we see is because Z had a standard deviation of 3 rather than of 0 or 1, the predicted probabilities have a lot more variability, right? You see that there are large peaks near 0 and 1. So in the chat, so I'm just going to give everyone participation credit for today because, you know, come on, I don't want to make anyone I don't want to punish anyone for being checked out right now. But in the chat, just state which variable you think is more informative, right? Which variable tells us more about whether or not a defendant will reoffend. X or Z? I'll go back and forth between these two histograms. There's the histogram of X predictions. There's the histogram of Z predictions. Which one, knowing which covariate tells us more? All right, you're not even being graded on this. Wow. All right, second time that I've really gotten y'all. Aha, Kyle, okay, so Kyle probably saw me go, wow. Yes, it is Z. Almost every single person was wrong on this one. Okay, so why, right? Why? Okay, so if the question that I had asked is which variable is more related to race, then the answer would be X. So that's not what I asked, right? I just asked which variable is more informative about your likelihood of reoffending. And what we can see here is that for the Z predictions, right, the spread of the Z predictions is much wider. So in both cases, right, I know that on average, everyone in this data set has a 0.5 probability of reoffending, right? The average for everyone, black or white, black and white, is 0.5. So the question is, once you tell me Z, right, pretending that Z is prior convictions or something, once you tell me Z, to what extent can I update my estimated probability of you reoffending, right? So for X, for over half the data set, right, for everyone that's white, knowing X doesn't tell me anything, right? I mean, if you're white and I know X, that doesn't tell me anything additional about how likely you are to reoffend. The probability, the estimated probability, is still 0.5. If you're black, right, there's some variability, but the variability is still, you know, most of those predictions are still fairly close to 0.5. So knowing X tells me a little bit, right, about how likely you are to reoffend, but it doesn't tell me a lot. Whereas for Z, right, most of these estimated probabilities are far from 0.5. I start out saying, okay, everybody's got a 0.5 or a 50% recidivism rate. But once you tell me Z, that tells me a lot. A lot for a lot of people, I'm going to be fairly certain that you'll recidivate or fairly certain that you won't. Yes, the response, is probably appropriate. Yeah, so think about that for a second here, right? The issue at hand is what happens before I observe this variable, right? What do I know before I see X or Z? All I know is that everyone's got a 50% chance of responding. Or even if I see A. I mean, let me real quick. I don't have this in my code, but I probably should. Let's do an AMOD, right? Let's take this guy, person, thing, model, do that, and then, so if I look at AMOD, right, there's gonna be a coefficient for A. You don't need to respond in chat, but think, what's the coefficient for A gonna be, right? I'm regressing recidivism on race, and we saw that the recidivism rates for both Black and white folks were the same, so the coefficient for A should be pretty much 0, right? It should be pretty close. If I look at a summary of, sorry, let me do the summary so you can see the p-value. P-value is, right, 0.6, right? This is not remotely significantly different from 0, right? So race doesn't tell us much at all here. I kind of forgot where I was going with this. I'm sorry. What were people saying? Okay. Right. So the point here is that race, right? Race is totally uninformative. Race doesn't tell me anything about how likely you are to reoffend. X tells me a little bit. Z tells me a lot. Okay. So here's the setup. I hope we all understand the setup reasonably well. So here's what we can do. Let's test, right? Let's test whether the X predictions for Black folks are significantly different from the predictions for white folks from both models, right? So we'll just do a t-test of the X predictions for Black versus white folks and the Z predictions. P-value equals 0.93, right? Not remotely significantly different. P-value, this one's pretty close, 0.05, but that happens due to randomness, right? These two means are pretty close to 0.5, right? The point is the predictions are not significantly different from each other. Okay, so, right, it seems like we're in a situation where fairness should be achievable, right? I mean, Black and white folks are recidivating at the same rates, right? They're reoffending at the same rates. The predictions, right, the mean, the estimated probabilities of recidivating from both models are the same, right? Seems like there should be no opportunity for an unfair outcome, except for this little thing right here, where the standard deviation of this variable depends on race. Okay, so let's get our prediction rule, right? Let's get our cutoff function, f, right? So let's let's say that I am pretty concerned with taking away people's liberty, right? I'm fair. I'm a hardcore libertarian, and so I only want to detain you, right, and keep you in jail if there's a really high risk of you reoffending. So let's make that cutoff 0.75, right? And let's look, right? Let's look at our histograms, right? And envision on those histograms where that 0.75 cutoff is. Okay, so before we do that, okay, so the first thing is, for different models, the average number of people that we detain will be different, right? For the X model, we're not going to detain that many people. We're detaining less than 0.5% of people, right? The mean of f of, right, I'm applying f to my X predictions, my model where I regress on X, and I'm detaining less than 1%. of people, right? Because I don't have that much information from the variable x. And so, right, so my predicted probabilities stay pretty close to 0.5. So not that many of those probabilities are bigger than 0.5. On the other hand, how about these z predictions? I'm detaining a third of people, right? I have so much more information from z. Plenty of those predicted probabilities from the z variable are greater than 0.75. So I'm detaining about a third of the people that come in here, right? So the choice of which covariates, right, I choose to account for in my model for determining who should get bail or get parole really matters, right? The choice of my cutoff really matters. I mean, here, let me expand the example a little bit. Let's go F0. Let's make this function. So you can probably take a second, right? You can probably guess how I'm going to change this, right? Let's say that I was a little bit less libertarian and I was very concerned with, so let's say I made the choice to detain a lot of people. So I changed this probability to 0.25. Then come on. All right, so then I apply the F0 function. It's going to be different now. Most people are going to be detained, right, under the X model. Whereas a lot of people, but certainly not all of them, right, under the X model, 99% of these values are above 0.25 down here. Whereas under the Z model, you know, there are a decent number of people who we still let go because we have a lot of evidence to suggest that those people will not reoffend. Right? So both my choice of which covariates to regress on when I decide who to give bail to and who to give parole to, the choice of covariates matters and the prediction rule matters. Okay, so there's legal and sort of societal and ethical consequences to how I choose those things. And by the way, sorry, I don't know if I said this, this happens, right? Courts all across the country use logistic regression models to decide who gets bail and who gets parole. So this is something that happens all across the country, right? This is happening right now. So these things matter. And the people in charge of this are not experts. They're not, I mean, I'm only sort of an expert, right? I'm just a graduate student who works on this stuff. But, you know, the people who are doing this are, many of them may not, right, have a grasp on these concepts that we're talking about right now, right? So, you know, this is a front, right, in the battle for justice, right? This is something that matters, and that, you know, if you're in a position of power, which being a software developer or a statistician is, you know, you have a choice here. Okay, so so how about fairness? Well, so let's go back to our F model, and let's see how many, right, what percentage of our detainees are black and white, right? So what I'm going to take is I'm going to index the variable A, which tells me race. I'm going to index that variable on which predictions were won, right? On who got detained, and I'm going to take the average, which will tell me the percentage of those people that were black. Okay, so for the Z variable, it's about 50%, right? Because the Z variable does not, race plays no role in it. For the X variable, it's 1. Everyone that I detain is black. We didn't need to write code to do that. We know that for the X variable, all white people have a value of 0, so that their predicted probability is 0.5, which is less than so that so that we don't predict any white people to reoffend. Okay, so we spent a while looking at code. Let's go back to this slide with new eyes, right? This slide, I think, probably makes a lot more sense now. We can see exactly how we got into a situation where the estimated probabilities for all the white defendants are 0.4, but there's a wide variability in black defendants' predicted probabilities of reoffending, right? And so, let's see. So for instance, how might this occur in real life? Well, it's possible, right? For instance, as you are hopefully aware, black people interact with the police a lot more than white people do. And so we may collect data, right? The process of collecting data, of collecting the number of prior convictions, right? The whole policing and criminal justice system is in part a data collection process. That process may be more informative, right? We may just get more information about black defendants than about white defendants, right? We may get a wider range of number of prior criminal convictions for black defendants than white defendants because they interact with the police more. And as you've now seen, the fact that there's a wider variability will contribute to this wider range of predicted probabilities. And then when combined with a prediction rule, right, could lead to this unfair situation where black defendants are detained at much higher rates than white defendants. At the same time, there may be other covariates out there, like Z, that are more informative, right? Z was more informative than X, right? Z gave us much more information about who would reoffend and who wouldn't, right? There could be covariates like Z out there that are much more informative about who reoffends and who doesn't. And if those variables are independent of race, then as we saw, we can get better information about who will reoffend and who won't from Z, and we can also get a fairer situation where the rates of detention for black and white defendants are more similar. So that's a choice that we make as statisticians, right? It's a choice when we were analyzing the Cora data set. We made choices of which covariates to put in that data set, right? It's the modeler's decision, right? And I mean, it may not be solely your decision, right? But the decision of which covariates to use in these models has ethical and legal and fairness consequences, right? So that's the moral of this example. Okay, are there any questions about this example? Fairly important, lengthy example, so hopefully go back and see that this person mowing my lawn is gone. They are, that's good. I'm thirsty here. Anything in the chats, feel free to raise a hand. Okay, not seeing anything. So moving forward, where's my, should be seeing the slides here. Okay, whoops. Okay, so moving on to a somewhat different topic, or same example but different concepts. So perhaps you're uncomfortable with the idea of an algorithm making decisions about people's liberty. If you are, you're not alone, right? This is a new idea, right? algorithms didn't make hardly any decisions 25 years ago, and now they make a lot of them, right? They decide what media you see and what ads you see, and who gets to go free after they're arrested. So the way this works in reality is that these algorithms make recommendations to judges who have the final say in what happens. And often the judges follow those recommendations, but sometimes they don't. So briefly, let's just talk about the advantages and disadvantages of this system, right? Maybe having the judge make that final decision makes you feel a little more comfortable. But if you're worried about, potential bias or discrimination on the part of human judges, maybe that makes you feel worse. I think or maybe having an algorithm do it as opposed to a judge, right? Just having a judge alone decide who goes free, right? That might make you uncomfortable if you're worried about discrimination on the part of judges. So the current consensus on the part of experts is that both tends to be a little better, right? So in the core example from a week ago, where we were trying to come up with different ways to analyze the text of questions to determine which ones were more or less likely to be trolls, right? I kind of said during lecture that this troll prediction algorithm would flag the questions for human review, right? So I kind of implied that, oh, we're not just gonna use this algorithm to automatically take down questions, right? We're gonna use this algorithm to help human moderators, right, moderate the data on Quora, or the questions on Quora. So this idea is called human in the loop. That's a phrase that you might have heard, right? Having a human in the loop when algorithms are involved in making decisions. So the disadvantages of having a human in the loop are that it's expensive, right? Facebook and Quora have to employ and pay humans to go through and read these questions. It's slower, right? An algorithm makes the decision in the blink of an eye. The human's got to go through, read the questions, right? Ponder the trade-offs and make a decision. Human bias, right? Conscious or unconscious, could work its way into the decision. And also human judgment errors, right? Humans just make simple calculation mistakes, right? They do things they didn't intend to do. Computers don't do that, right? Computers do exactly what you tell them to do. The advantages, right? The primary advantage is that having a human in the loop helps make the process transparent. The best prediction algorithms right now are deep neural networks and boosted random forests and very complicated these are complicated machine learning algorithms that it's impossible to explain how that decision got made. I mean, the linear models and the logistic regressions that we've seen in this class are the simplest possible prediction algorithms, and as you've seen, they're not easy. Right? You gotta have a degree. You gotta take classes, right, to be able to understand, how these models are making these predictions. It's basically impossible to understand how a deep neural network is making these predictions. So the transparency, right, is important. And then also machines and humans can kind of temper each other's biases. So there's a recent paper out that shows that judges will often extend leniency to younger defendants, right? Somehow, if you're young and you committed a crime, right? We have this idea that you're just a little less liable for it, right? That perhaps your judgment wasn't quite as well developed. And they also incorporate kind of other circumstantial information. Right, and so if they're doing this in a way that's not biased, right, then it's nice to have the judge in the loop there to use this information that is maybe too fine grained for the algorithms to use. Okay, so we're getting close here. So there's a couple other concerns, and then we'll do kind of one final example to drive the points home. Okay, so other concerns, this is a huge one actually that I haven't talked about much, but biased labels, biased outcomes, right? Biased why. In the previous examples, training data, the label we have, right, is reoffense, right? So it's whether or not someone was convicted of committing the same crime that they had been convicted of before. Is that the label that we want, right? Not quite. What we actually care about is whether they reoffended in reality, right? Convictions can be wrong, right? I mean, people are every day, you know, let go or found not guilty for crimes they actually did commit, and they're also found guilty for crimes they didn't commit, right? The label of whether or not someone was actually convicted is different from whether or not they actually reoffended. And what we want to know, right, when we're determining whether someone's safe whether it's safe to release someone on bail, is whether they're actually at risk for reoffending, not whether they're at risk for being convicted of reoffending. So the labels are not exactly what we want. And if one group of people was more likely to be caught, right, or convicted of committing crimes than another, right? Maybe they are, right, they're just more likely to be convicted when they didn't really commit the crime. Or if another group, right, so the idea here is that Black people are more likely to be convicted of crimes that they didn't commit, perhaps, and white people are more likely to be, you know, released or found not guilty for crimes they did commit. If that's true, then the very labels that we're using to train our model are biased, right? And there's no way to detect, there's almost no way to fix that, right? If your model is based on data that itself is biased, the model is basically going to hopelessly be biased. It's very difficult to correct for it. The other problematic situation is a feedback loop. So some algorithms are one-off, but most are not, right? In the long run, these recidivism algorithms are feedback loops, as people who had decisions made for them by a recidivism algorithm, right, perhaps reoffend and come back in and have an offense prediction made for themselves. So a more concrete, immediate example of that is that algorithms are used to dispatch the police. And one pretty easy way to decide where to dispatch police is to see where more crimes are committed, right? To try and figure out where more crimes are committed and dispatch more police there. Of course, if we dispatch more police to an area, right, it's not necessarily that more crimes will be committed, but certainly more crimes will be discovered, right? The more police we dispatch to an area, the more people are going to be arrested and found guilty and found committing crimes or what have you. And areas with less police presence, the crimes that do happen are less likely to be discovered. So over time, right, this is going to be a positive feedback loop. We dispatch the police to areas where we perceive there to be more crimes. We see a lot more crimes because there's more police there. We dispatch more police there, right? It's pretty simple. Don't need to be an expert to see that happening. But this is a real problem that happens, and algorithms are used to dispatch the police, right? So this is an example that's a little different from most of what we talked about today and on Monday, but yet another fairness concern for algorithms. Similarly, Amazon, you may have read about this last year. Amazon tried to train a recruiting algorithm, right? That would be a really useful thing for a company to have, is a machine that can determine who's going to be a good worker, right? Who's going to be a good fit for their job. So they tried to have an algorithm to determine who, to basically sift through resumes and decide who would be good hires. But historically, hiring had been sexist, right? Amazon hiring managers had been more likely to hire men than equally qualified women. And so the data, right? The outcome, like the y equals 0 or 1, right, is whether or not someone was hired or not. it was biased, right? Women were less likely to be hired with equal qualifications. And so the algorithm simply learned that ingrained bias. And so, in fact, in that algorithm, it was a very complicated machine learning algorithm, but the researchers at Amazon interrogated it, and they found things like if you had been captain of a lacrosse team or a men's lacrosse team, that made you more likely to be, that had the algorithm predict you to be a better candidate than if you'd been captain of a women's lacrosse team. Right? Just blatant ingrained sexism in the prediction algorithm, right? And that it's not because, right? And that sexism isn't because you maybe see news articles on this sometimes, and they're like, oh, it's like machine learning racist or whatever, or or algorithms like out to get you. No, they're not, right? The algorithm is implemented by humans, and it takes in data, right, that was created through some process, and the algorithm simply reproduces, right, whatever historical sexism or racism or other bias may already exist in that data. Right, so the responsibility for these things lies with us, right? It lies with the people who implement and deploy the algorithms in the real world. The old adage for this is garbage in, garbage out, right? You give me terrible data, my model makes terrible predictions. You give me unfair data, my model makes unfair predictions. Okay, so the final example that I'm going to go through is one that is probably pretty important to UW students. So we're just going to talk about quantitative fairness and affirmative action. And what I'm not going to do here is I'm not going to take any stance on affirmative action, but what I want to convey is that the conceptual framework of quantitative fairness can be applied to problems like affirmative action, right? Highly controversial problems, right? Problems that are controversial even at a liberal institution like UW. That the quantitative fairness, right, framework allows us to analyze these situations in a more rigorous way than they typically are. So let's talk about two opposing kind of common perspectives on affirmative action. So a strong anti-affirmative action stance, right, just states that you should not use race in an admissions decision, right? You just simply should not take account of the applicant's race when deciding whether or not to admit them into university, right? And we saw at the beginning of lecture on Monday that this doesn't necessarily always lead to a fair situation. We also saw that it can lead to fair situations, right? There certainly are times when not using the sensitive attribute leads to a fair outcome, like in the translator hiring example. Okay, so this is fairness through unawareness, right? So pretty easy. We can just take this language from quantitative fairness and apply it to this affirmative action stance. The quantitative fairness term statistical parity is what we would use for the stance that universities should admit all groups at roughly equal rates, right? So it's the idea that, well, well, this is not how it works in the real world, but if Black, Hispanic, white, and Asian people were all applying at the same rates to a university, all at 25% rates, then they should all be admitted at 25% rates, right? We should just take the best 25% candidates from each of those groups. So that's a very strong, right, pro-affirmative action stance. And these two stances are kind of fundamentally irreconcilable, right? I mean, the first stance says completely ignore race. Of course, your outcomes aren't going to be independent of race because the other things that you consider may be associated with race. But don't take it into account directly. Whereas the second stance is saying take race into account as directly as possible, right? Make everything equal for people of both races. Okay, so you may, I think it's probably fair to say that that there's people in both of these camps, and they shout at each other a lot, and not a lot gets productively decided, right? I think I'm willing to claim that. How can we do better, right? So we've already named the problem using quantitative fairness, right? We already kind of have a nice understanding from the fairness perspective of why these two stances are so different, why it's so hard for these two groups to come to an agreement. Okay, so now, right, let's consider one of these diagrams that we saw on Monday. Right, and we haven't talked a lot about these diagrams, but remember, just kind of think of the arrows as being arrows of causality. So this is a very simplified diagram of the affirmative action situation. So here we have race causally directing educational prestige. So what that means is that your race in some way determines the prestige of maybe the high school that you went to, right? I think we can all accept that because of historic inequalities based on race. Black people are less likely than white people to have gone to, say, prestigious private high schools, right? Like, I don't know, Exeter or Collegiate or something. And similarly, we could imagine that race affects your academic interests, right? When you apply to college, you say, oh, I want to be an engineer, or oh, I want to be a philosopher, right? And those things may also differ by race for a variety of reasons. And then these two factors are accounted for in the admissions decision, usually. Right, and so and race, this dotted line shows that race may or may not be accounted for. So thinking about this, we can see that there's maybe a middle ground between those two perspectives that we saw on the previous slide. So the first perspective, fairness through unawareness, would say that we should get rid of that dotted line, that we should still take into account educational prestige and academic interests, and acknowledging that those things may differ by race, right? And so the fact that Black people may have gone to less prestigious high schools on average will lead to fewer Black people, a lower admission rate for Black people than for white people, but that we simply should not use race in the admissions decision. The second group, right? The second group says, well, whatever inequalities there are in educational prestige and academic interests, right? Whatever racial inequalities are in there, we should correct for them by directly considering race in the admissions decision. So that group is saying we should fill in that black line, right? That black line from race to the admissions decision should be there, right? So that educational prestige and academic interests may still affect the admissions decision, but we're going to take into account race as well to correct for any racial inequalities in those two variables. So those are two of the most extreme perspectives, but there's another option, right? So one could argue that that the prestige of your high school maybe isn't all that relevant to the admissions decision, right? Maybe, I mean, we have other things. Maybe we have your test scores and your essay and your AP test scores, right? Why do we need to take into account how prestigious your high school is? We have all these other measures of how likely you are to succeed in college. Maybe we think that the historical racial inequalities in high school prestige are basically invalidate that variable, right? So we could not account for or we could use educational prestige, but account for racial inequalities in educational prestige. On the other hand, maybe we think that academic interests are a pretty crucial factor in admitting students to college, and so we could argue that that it's important to get the right mix of students with different academic interests, and so it would be unfair, right, to account for race or to correct for race with respect to academic interests. It would be unfair to correct for racial disparities in academic interests when we're admitting students into college, right? So this example, right, could be very broadly extended. I mean, there's not just two variables in between race and college admissions here, right? There's a whole 18 years of your life, right? There's all sorts of things. There's your socioeconomic status, there's your parents' educational status, there's any number of things. But using, right, the quantitative fairness framework would allow us to think through and ask questions like, which of these variables are we willing to accept racial disparities in, and which ones aren't we, right? For which variables is racial disparity something that we have to accept, and that correcting for it would be unfair? And for which of these covariates, like perhaps high school educational prestige, is the racial disparity unacceptable, and we have to correct for it? Okay, so I haven't written any code for this example, but right, but I'm guessing that this is a topic of some importance to y'all as students, and so you can see here how the ideas that we talked about this week could be applied to this problem, to perhaps improve the dialogue around this decision, and maybe even come up with a solution that is a compromise solution that's acceptable to people with strong varying opinions on this. Okay, I think that's all I got. Oh, no, it's not. Okay, one last thing. Okay, so the boilerplate for this is that it's important to realize that that none of this quantitative fairness stuff stands in for or replaces or really corrects for fundamental issues of justice, right? So given that Black people are policed more aggressively than white people, there's no way of correcting that with an algorithm, right? There's no way of tweaking our, right? We can't tweak our recidivism prediction rules to sort of fix that, right? This is not a panacea. It does not, right? There's just getting in there with some code does not solve the problem, right? So keep this you got to keep this in its place, right? Solving problems like inequality and racism in the criminal justice system. You're not going to do that with an algorithm, right? You're going to do it politically. You're going to do it through various forms of activism. So take this all with a grain of salt. Keep it in its place when you think about maybe the events of the last week and about how you're going to engage with these issues going forward. Okay, now I'm done. Yeah. So first, if you have any questions about this stuff here, I'll share screen again so you can see the thing. Here's a good slide to stay on. So yeah, if you have questions, put up a hand, type them in the chat. I'm gonna drink some water real quick, but yeah, go for it. There's no email or chat participation questions today, so no worries about that. Let's see. And before I start answering questions, the rest of this, we've only got what? Oh, Dang, I'm sorry I went almost the whole time. I thought I was going to take about an hour, but I went 10 minutes over. So I'll stick around till 5 to take questions about the project, right, or anything else, but particularly about the final project. Okay, so let's see what we just got asked. Okay, yeah, glad to hear it. I'm hopeful that a few of you, that more than a few of you, really got something out of this. I think it's important to spend a little bit of time on ethics in any kind of stats or applied computer science or classes like that, and particularly at this moment in time. Yeah, I'm not seeing any other questions. Let's see. Okay, so I'm gonna stop recording. And